Sebastian. Thank you very much for the introduction and welcome to my talk. This is joint work together with Dr. Sternin, Jessica Grahn, and Adrian Owen. We are interested in using music imagination to drive EEG-based brain-computer interface. Like this, I give you two well-known music pieces, and I will ask you to imagine music piece A if you want to say yes, and music piece B if you want to say no. And if I can do this, I can ask you yes/no questions and read the answer from your brain. And if you could do this, we could build a brain-computer interface to communicate with locked-in patients. So that's our ultimate goal. For now, we're just working with healthy participants to figure out whether that could actually work. So what I'm going to do is I'm going to use deep learning techniques for the pattern matching part in this scenario. Now, deep learning has become very popular in the last years, but not so much for EEG. And there are several reasons for this that I see from my point of view. So one is that it's really hard to use these techniques if you are not a computer scientist. It's very technical. It's very hard to start using that. And on the other hand, for people developing these methods, it's not really interesting because there are hardly any data sets out there that you can use for development. So I would like to address these two issues, and so we've recently published the OpenMIR data set. This is a data set of EEG recordings of music perception and imagination. It's published as public domain, so everybody can use it without any restriction, and it's covering 12 music stimuli. And in the following, I'm going to use this data to develop deep learning techniques. Now, just to be sure that we are on the same page concerning deep learning, I'm just going to give you some basic information on these techniques. So first of all, in machine learning, we distinguish usually between supervised and unsupervised learning. So in supervised learning, we have data with labels, and we are trying to learn a predictive model that gives us labels for data we haven't seen yet. So this is usually classification or regression, as we've seen earlier today. And on the right-hand side, we have an example for unsupervised learning. So we have some data without labels, and we're interested in structures within that data. So for instance, in this example, we could find these three groups, but this depends always on the number of groups we want to find. So for 5, this would look very differently. Now, our typical machine learning workflow for classification would be we have some data, we extract features using handcrafted feature extractors, and then we feed these features together with the labels of the data into a trainable classifier. This will give us a model which then predicts labels for unseen data. Now, in this workflow, a lot of work actually goes into developing these feature extractors. And usually this also requires a lot of knowledge from experts. Now, in deep learning, what we can do is have trainable feature extractors. So we're getting rid of the experts, basically. Not really, but there's far fewer work on the feature extraction part, but this is part of your learning pipeline. And the nice thing actually is now that we can pre-train the system using unlabeled data, which is usually much cheaper to get, and in most cases really abundant. And thanks to high-performance computers and graphics cards, we can also deal with large amounts of data here. Now, the technique that I'm going to use in the following is based on convolutional autoencoders, and those are this is a technique that combines two popular ideas from deep learning. One is autoencoders, and the other one is convolutional neural networks. Now, an autoencoder is an artificial neural network that has neurons, the dots here, organized in layers and connections between them. And this network does nothing else than reproduce its input. So we have some input that goes into the network, and the network is trying to process the data in a way that it reproduces the data. Now, to make this non-trivial, we're actually forcing the network to go through a bottleneck, or we distorting the input to make it harder to reconstruct. Now we can train this without any labeled data. This is just like putting the data in, getting the data out, measuring the error. And we can also stack these models. So once we've trained one layer of autoencoder, we can also increase the complexity of the features and further compress them. Once we've done training, we can replace the decoder part, so the right-hand side of the network, with a classifier, and then train the whole system, including labels. So this is now supervised learning. and we don't need as much data for this. Now, in this kind of network, you see that all the neurons of neighboring layers are fully connected to each other. And in convolutional networks, this is different. So we don't have full connections, but we have only local connections. And in convolutional neural networks, each of the layers applies two operations. The first one is a convolution operation, where we have a kernel or filter matrix which is moved over the input, and for each position we compute an output value. And these output values are then, or neighboring output values, are then aggregated together using a pooling function. That's the blue function here. And usually this is a maximum. Now this structure is basically motivated by the visual cortex. But you can also think about it if you use, it's like you use a graphics filter in Photoshop, let's say. But the difference here now is that these filter weights are not predetermined, but they're actually learned. And it's not only one filter, but there are multiple filters that are applied in parallel. Now, if we combine these two ideas, convolution and autoencoding, we get a convolutional autoencoder. So in a convolutional autoencoder, we use convolution in the encoder, and then have to use a reverse operation, that's deconvolution in the decoder. I won't go into the technical details here, but it's actually quite simple. You can train this like a normal autoencoder using unlabeled data, and then you can replace the decoder again with a classifier, and you get a network just like this one shown at the top. All right, so I am going to use this technique now to identify patterns in EEG data. And so the first thing we can do, for instance, is try to learn spatial components in the EEG data, much like you would do using principal component analysis or independent component analysis. So here we've used the data from our data set, just the perception data, but combined from all participants. And we've used a convolutional autoencoder with 4 filters. So we can learn 4 filters. Each of these filters gives us one of these spatial components, here visualized as topographies. And for comparison, on the left we have the PCA result and the ICA result for comparison. And below we see the reconstruction error. So how much information basically do we lose if we compress 64 EEG channels that we had originally into 4 components. So the lowest error is obtained for the PCA, but the error for our convolutional autoencoder is also pretty small. Now the nice thing that we can now do is we can use this globally trained convolutional autoencoder as the initialization to learn models for each specific individual. So this is kind of personalized dimensionality reduction, and the components that we will get are also linked together because they come from the same origin. So this is what they look like. So again, this is the origin, the initialization, and then we have personalized versions of this for each specific individual. And so you see they're kind of similar still, but you can also see the individual differences. And similarly, we can do this for the imagination data, and so they're quite similar, the components that you get. To give you some idea of the reconstruction error, here is one example where it didn't work as well. So the reconstruction error is actually twice as high as on average. The input mean, so what we feed into the network is in red, and the reconstruction is in blue, and in the background you see the individual channels. And below you see the waveforms from these 4 components, and those can now be used as features in a classifier. So as a quick solution, we basically build a classifier on top of it. So the first layer is fixed. That's the components we've just seen on the last slide. We added another layer that can now learn more complex features on top of these components. So you have one axis of your data is basically the 4 components, the other is time, and it will learn features on top of this. In the end, we have a classifier, and we train this using the labeled data we got in our data set. Now, these are the results that we can obtain with this architecture. So if we want to try to classify which music piece it was that people listened to, we can get the accuracy close to 20%, with a chance level originally of 8.3%. If we try meter classification, where the chance level is 50%, we reach almost 66%. We couldn't find any significant results for classifying lyrics versus non-lyrics. So this seems to be much harder to figure out. All right, so this is still this is already very promising, but it's not enough to run a brain-computer interface based on this. So we've looked into more advanced encoding schemes, and the first one I call cross-trial autoencoder. Now, in this case, we are not trying to reconstruct the input, but we are trying to reconstruct a different trial from the same class. So this makes the situation much harder for the autoencoder, and we're forcing it basically to learn features that are common across trials with this. Now the nice thing also is that because we're now training with pairs of trials, we're actually increasing the number of training examples combinatorically, which is quite helpful if you only have a few trials, as in our case, per class. But what we actually want to learn are features that help us to distinguish between classes. Now, for this, we have to take into account also trials from other classes, and we can do this in the following. We can basically demand that two trials from the same class should be more similar to each other, given those features, than two trials of other classes. So we can define constraints like this, and there's a whole literature in machine learning that focuses on learning metrics for distances and similarities with such constraints. And now I'm going to show you how we can do this using our autoencoder approach. So if this is our original convolutional autoencoder with the encoder part using convolution, the decoder part using deconvolution, we're only interested now in the similarity of these features after convolution. So we can get rid of this part. But now we have to process 3 trials at a time. So we have to replicate this pipeline. One for the reference trial, one for the paired trial from the same class, and one from the other for the other trial from the other class. And now we're going to compare the reference trial to the paired trial and the reference trial to the other trial, and we get 2 similarity values using Pearson's R correlation. And then we're going to predict the value that's higher. So that's using so-called softmax layer. And we can learn the convolution step basically by minimizing the constraint violations. So how often do we predict the wrong trial? We're trying to minimize this number. And just as a reminder, that's basically our former encoder here hidden in these 3 pipelines, which are basically identical. Now with this, we can build a full workflow using all the methods I've shown you previously. So we start with a basic convolutional autoencoder using all the data of all participants. Then we personalize the result to the specific subject. And then in the third step, we train with the pairs. Up to here, we haven't changed anything about the architecture of the network. We only trained with different data. And in the fourth step, we're going to change the structure of the network, as I've shown you on the last slide, and train with the triplets. As an example, we're going to look at subject 14. We try to predict the 12 stimuli. And we're going to use 4 filters, but this time they are going to be 2-dimensional. So instead of looking at 1 sample over all the channels, we're going to look at 5 samples, so a time window of 5 samples over our channels. And these are the filters that were learned. So on the left, you see the mean over all the time steps, and then you have the individual time steps for the 4 different filters centered around the filter center at T0. So with these filters, the trials from the same class are more similar in 89% of all training cases and in almost 70% of the test cases. We can increase that number if we use more complex models with more filters, bigger time windows. We can get up to 73.3% for this participant. And in general, if we look at the other participants, we're always between 70 and 75%, which is already pretty good, given that we also only work with 5 trials per participant. And but that's still not enough for the BCI setting. So what are we going to do next? So I'm working on a method where we can use the full data from all participants throughout the whole workflow, which is much more complicated because you have to take into account the individual solutions in the first layer. And we're also running several other experiments increasing the amount of data that we have in the CogMIR dataset. So coming back to my initial slide, what I've shown you today are the first tiny steps towards addressing these two issues. So if anybody of you is interested in collaborating or contributing, this is my contact information, and here's a link to the code and the data set. So thank you very much for your attention, and I'm happy to answer questions.
The reconstruction error you were showing against PCA back in the beginning when you were first talking about convolutional autoencoders, it seemed like PCA was still lower error.
Right.
Why do you think that is?
So neural networks are usually not finding the optimal solution. They find a local optimum. So you get really easily stuck somewhere where it's not like the global optimum. Theoretically, they could be PCA, because PCA is fully linear only, and in the neural networks we have the nonlinearity, so they could perform better in terms of model complexity. Maybe we could see that if we used more training data, but I mean it's not a terrible big difference. Actually.
How many examples are you using?
So if we're looking at combining all the data from all the participants, we're looking at like 5 hours of EEG recording.
You preface this with an application,
yes.
Which maybe is not very linked to music cognition or MIR. Do you have some thoughts about how this data set could be used within the MIR community?
Well, what you could do, like, I didn't talk about the data set because this was like really beyond the time I got. But basically what we did is we tried to sample the space of musical pieces systematically. So we have like half of the pieces in 3x4, half of the pieces in 4x4. We have different genres. We have classical music. So we have pieces with and without lyrics, same piece, but one sung version, one not. And so there's things that are interesting from an MIR perspective too, and to see like what's different in the EEG when these things are present or not might really be interesting also to think about like how did we represent these features in MIR basically. So I mean it's just a small set in terms of the number of stimuli. You should probably go like much wider if you want to have something valid in the end. To be able to say, okay, like if you have a 3x4 measure, we usually see something like this, and like pieces are more similar in this domain based on this feature. So this is not our like primary objective, but
one
you could
thought
something.
is to maybe, and maybe you've got many thoughts, and this is one that you discarded along the way, but one thought is to collect some cognitive data on these pieces as well, because that's closer to what you might want to mine using near features. So if you can link those cognitive appraisals, whatever they are, attention, emotion, complexity, groove, catchiness, whatever it is, to some of those, that could be interesting.
Yeah, so one thing we are planning to do, we haven't started doing it, is actually just doing a simple perception experiment where we just ask people to rate what's the most similar one, like give us a ranking, because this can also help us if we look at the confusion matrices of our classifiers in the EEG domain. We might see patterns that we also see in the perceived similarity of the pieces. So two pieces that are perceived similarly could also be similar in the EEG. Could be, must not. Doesn't have to be.
One more question and then we'll move on. So go ahead.
So I just have a very quick question. So you mentioned about these two kind of music with lyric or without lyric. Did you have any preliminary results, and what's your observation?
Yeah, so as I said, it's really hard for us right now. We didn't get a grip on trying to distinguish music with lyrics against music without lyrics, at least in the EEG. well, we have to say that the EEG is very bad at localizing things. So I would expect that this is more something you would see like spatially, like that like the language area maybe is active during lyrics perception, whereas it's not active if you're just listening to an instrumental piece. Now the thing is, because these were all popular pieces, we can also expect people to sing along like involuntarily, even if there's no lyrics in there. So that could also be an effect that's kind of blurring results. So it's really hard to say right now, but we cannot distinguish them yet.
Thanks for your
Thank you.